So I'm gonna finish up number 2, and then we'll go back to number 1. Number 3 should be the easy part. That's the shortcut to what we have to do in number 2. So I've got all the parts I need here. I'm going to show you some notation that you can use here. Let's see. I'm going to go ahead and multiply these guys out so I get negative 27 squared over n squared, n cubed, plus 27i over n squared, plus 12 over n. Yeah. So if you want to, for me, just to show you something I did as a student, this is always going to be the limit as n goes to infinity for any problem like this. It's the definition. This is always going to be sum from the first rectangle to the nth. Always. So what I kind of started doing was I used this as a little shortcut ways of writing that. So it's the L of the sum, the limit of the sum. Let me go ahead and write each of these separately. So again, the major thing to realize is n is a constant according to the sum. And so is any constant. So I can rewrite this as negative 27 over n cubed, sum of I squared, 27 over n squared, sum of I. And then this doesn't really matter. I kind of do 1 over n sum of 12. Leave the constant in there. Doesn't matter. So now I can use those rules. The sum of I squared, that was the weird one. That was the n plus 1 to n plus 1 over 6. That's this guy. Plus 27 over n squared. This guy was the nice one, n plus 1 over 2. Plus, this would be 12n times 1 over n is 12. How are we doing so far, you guys? Please let me know if you have a question. Can't see where something came from. This is weird, but this is still a problem that you can sink your teeth into. It is basic math, but it's built on top of weird shit. Infinite rectangles. Yeah, that's weird shit. Right? So I know there's like 2 levels of this that's always in your head. It should be easy, but it's weird. So, you know. What happens to this? In the limit. Yeah, it goes to 2. Because the degrees are the same. So it's the ratio of the coefficients, so that's 2. So I get 1/3, so I get negative 9 for that. What happens to this? Goes to 1, so I get 27 halves plus 12. Yeah, and then if you remember, if you plug the function into your y1 in the calculator, you can actually calculate the integral. And it does come out to be 16.5. It's a nice way to check your work. Check. So, going back to number 1 now. Number 1 compared to this is easy. What would delta x be for number 1? It was using 4 rectangles, right? 4? Yeah. So what's delta x? 3/4. I like it. So then, if I gave myself a little, I gave you a picture, right? Yeah, I did. So here's 0. Here's 4, right? Yeah. And I told you to use left and point 2. So you can kind of draw all this in, blah, 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 blah. Wait, I'm supposed to use, yeah, there. 3/4. Oh, it gets a little gross, but I won't. 3/4. And then add 3/4, I get to 1.5. Right, so it's going to be there. and then I get plus 3/4, 2.25, and then 3/4 gets me to 3. I like it. It's always satisfying to have the rectangles fit. It tells you you've done things right so far. And then it really is, what I always do, we do this. Notice, couldn't you pull this out? 3/4 times f of 0 plus f of 3/4 plus f of 3/2 plus f of, where was I, 2 1/4 plus f of 3. Yeah, like 3. I stopped there. There you go. So you make sure you got the right number of rectangles. Right? 1 to very far. Yes, no, maybe so. Every single one of them is times 3/4, so I can pull a 3/4 out. So it really is just a bunch of figure out what the function values are, add them up, multiply by 3/4. 3/4 times 4 plus whatever the shit. Do it all in the calculator. And what do you end up getting at the end? What'd you get? 15.9? Did anybody else get anything?
I got 17.2.
17.2?
That's 16.2.
Neat. All right. I love it. We got 2 people that got 16.2.
I got 16.2 one. It might be how you
Say again?
It might just be how you
Oh, no. Yeah, when you're doing this, if you round, your answer is going to be off. I would not say that these are approximately the same. No way in hell I would say these are. So how do you do this step? Do it in the calculator. All right? Figure out what all those function values are. Don't round at all. Look at this. You can use the table function even in your calculator. Put the function in the y1, use the table. Whatever you got to do. So more than likely, this is the right answer here. It sounds like the other ones are rounded way too much. Ooh, there you go. And in fact, I mean, considering it's a symmetric region, just doing that by itself should be a decent approximation. So that's really close to this. Yeah. Okay. So that's number 1. Number 1 is very concrete. It really is, what's the area of this rectangle? What's the area of this rectangle? And then you add them all up. That's all it is. That's it. That's it. Don't get so wrapped up in how we capture that idea in this general way. Functions almost always make it seem harder than it really is in any specific situation because they have to be generally true for an infinite number of situations. Okay. And then the last dude, what is the antiderivative of this thing? Yeah. So here's the idea. We're about to get in, let me see. Well, let's first do this, and then I'll show you why the plus c goes away. It kind of leads into what we're about to get into. We haven't proven this connection in general. We haven't proven the connection between this symbol only means the area under this curve from this to this. That's all this symbol means. But it does seem to be connected to the antiderivative of the function that's inside. We haven't proven that connection yet. And yes, we will prove that connection. We'll all go a little more insane. But when I plug a 3 in here, I get negative 9, right? 27 divided by 3, plus 27 divided by 2, plus 12. That looks very familiar. Catacooth. Yeah, same thing, of course. I like it. So again, that's not a proof, but that makes it really strong evidence that the antiderivative function is related to this whole process here. Like it. Now watch. Now watch. Here's the. We're gonna do just a little bit more. Has everybody got what they want in here? I'm sorry. All right. Do you remember? It was a. I didn't make this step as big as I could have because I think it's dumb to do it. The book makes this step huge. One section in chapter 2 was, here's the derivative at a value of x, like 2. And they made it seem like it's its own thing. And then the next one went, here's a whole new process where you just get the derivative everywhere. And I kind of just went, get the derivative everywhere and then plug 2. Check. Everything we're doing so far is specific between this and this value, right? And then I try to give you a little bit of a taste of what that process would lead to if I made this one endpoint whatever I wanted to, x. We did that whole process. So here's something kind of nifty. Let me just write this down. So this is a function in its own right. In fact, let me be a little careful. I've got to be very careful. You can never have this variable the same as that variable. That gets really strange. You can't have the area changing and the function itself changing according to the same variable. That's funky shit. So this means there's some function that exists, f of t. Cool. Some function exists. And then I'm saying that g of x, what does g of x represent? Fundamentally, what does g of x represent? What does this do?
Area.
Finds the area. So g of x is the area under the curve from a to some x. Some x. So just like the derivative function is a function in its own right, this area function is a function in its own right. Now here's something that's really, 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 really cool. First thing is I want you to realize, if I wanted to know, if I wanted to do this, here's the reason why when I do antiderivatives the plus c doesn't show up. So this, let me see if I can do this. If it was, I don't want to say this. So here I've got my function. I'm going from A to B. Right? So if I was, so by itself up to A, what would this be? Think about it. The integral under the function from A to A. 0. I'll let it. So the antiderivative, though, would be plus c, right? Okay. Now, up to b would be the area up to b, 11. So, and the antiderivative up to b would be f of b plus c. Okay. But then you take the difference between the two of them, and the c's cancel. Now we're going to get a little deeper into that. I'm trying to do this a little too early. But there is a reason why the c's don't show up when I'm finding a definite integral, a definite area. It's because the two c's would cancel. So we're going to get there. Try to do that a little too early. This guy. This is where things get really flippin' cool. All right. This is its own function. So, for example, if the function looked like this, as I move, what would happen to g of x? Would g of x be getting bigger or smaller? So this is like the point x1. G of x1 is some area, right? Is this area of this. Here's x2. Is G of x2 bigger or smaller? G of x1 is the area from what to what? A to x1. So it's this area. G of x2 is the area from A to x2. So it's all of this. Bigger. So how I make the area start getting smaller is my function would actually, my function would actually have to go under. That's that idea of negative area that some teachers shy away from. But again, if I think of like flow, cash flow, if the cash is flowing into me and I know the flow rate, I can figure out the total amount of money I'm going to make. It's going to be fine. If my flow rate starts to go the other way, oh shit, right? Which is normally the way it is in college, then I'm going to get negative results. Ooh, who gives a shit? That's because it's flowing away from you, right? So negative area isn't an impossibility because now we're realizing area means more than just here's a square and here's the area. It actually means total amount of, considering flow rates and stuff. Okay. So, what I'm really curious about right now is, what the shit is G prime? What's the derivative of this? So, how do we, oh, you're gonna love this shit. How do we figure out derivatives when we're not sure? We have to go back to the limit definition, right? Okay. So what if I went, just stay with me now. I'm going to over-exaggerate this, but we know that the h eventually goes to 0, so it's a very small step. Just so we can see it, I want to do this. So G prime of x should be how much the area will change if I take a little bit of a step forward. Like how much area will I add in? And the really neat thing is, I want you to realize, let's try to set this up. So this would be G prime, would be the limit as h goes to 0, G of x plus h minus G of x all over h. God, none of my markers are red markers. That's just what the derivative is, right? Back in the day. G of x plus h minus G of x. How much difference is there here? How wide is this? Yeah, it's h. H wide. Is that cool? And how tall is it? Yeah, G of x, right? In fact, but be careful. What is this? What is this function? It's f of t, right? So how tall is this f of x? Why f of x? Because what is h doing? H is going to 0, right? That's what I wrote there. Give it 0. Stay with me now. So the height isn't x plus h because eventually that h is going to 0. The height is going to be f of x. So what is G of x plus h minus G of x? Here's G of x. Here's G of x plus h. The difference would be the area of this rectangle. And what is the area of that rectangle? Well, how tall is it? We said it's f of x tall. It's f of x tall, and how wide is it? H. What happens to the h's? Cancel, so I get f of x. So let's really see what the hell just happened. Stay with me. This is really flipping cool. The derivative of the integral is the function itself, evaluated at that point. The derivative of this integral is the function itself. All right, let me write that down. So if I have integral a x f t dt, this derivative is f of x. So g prime of x equals f of x. Oh, get out of there, big SF. Think about big SF. Yes?
Where is it, f of x?
F of x.
coordinate like on the top one? Like is it the function inside?
Yeah, this is t. Yeah, that's t. Let me write it better. Is that cool? Okay.
Yeah, no, I mean like, so the f of x is for the area, or is the x meant to be a zero?
No, right here. Now be careful. This difference is the area of this rectangle. Is that cool? This difference is the area of this rectangle. And the area of this rectangle was h times f of x. Because that's where this thing stopped. So if I go one little infinitesimal step out, it's building off of f of x. Like it. So this guy is its own function. And then we said, is it differentiable? Can I find the derivative of it? Yes, I can. Which this kind of reinforces on its own. If g prime is little f, g should be the antiderivative of f. Ah, yes? Reinforces that g of x equal to integral a to the x f of t dt equals big ass f of x somehow. Approximately, let's say, for right now. If the derivative of the integral is the function, then the integral itself must be the antiderivative of the function, which is what we were saying before, which is that step 3 on the handout we just did. Now, related to this, I love thinking like this, but let's see if you guys, if I put a piece of tape on this, how wide is tape? Not very. It's a really good human way of showing dx, the width of a piece of tape. You guys with me? A little bit? Now, any chemists don't come at me with, well, that's actually, screw it. To a human, that's flipping barely existent. So if I put a piece of tape on here, how much is it? It's f of x. That's how long it is, isn't it? So that's what it's going to add to the area that's there already. So for example, the circle. Right, let's say. And if I put a piece of tape all the way around the outside, how long is that piece of tape? 2 pi r. Yeah, so put a piece of tape all the way around the circle. It's 2 pi r long. That should be the amount that it adds to the area of the circle. So that should be the derivative of the area of the circle. It's how much the area of the circle changes if I put a little dr, a little piece of tape around it. That should be how much it changes. What's the area of a circle? Pi r squared. What's the derivative of that with respect to r? 2 freaking pi r. Flipping awesome. So that's why I'm sure you guys have noticed, I think maybe it came up in here once or twice before, that the derivative of something like pi r squared is the freaking circumference. That's why. How much, if I went out just a little bit, how much would the area change? By the circumference, because that's how much you would actually gain, that little piece of tape. Oh, I love that idea. I know I'm weird. Okay. All right. Let's see. One last thing and then I'll let you out of here. Just to kind of reinforce this by itself. We still got some more work to do before we could officially do this. This is unofficial at the moment. This, by the way, this together here, this is called the Fundamental Theorem of Calculus Part 1. So I affectionately call it F-Talk. F-Talk 1. Thankfully, there is an F-Talk 2. Unlike History of the World Part 1, there was never any Part 2. If you don't know what History of the World is, Google that shit and watch it. It's awesome. So there will be an F-Talk 2 in our future, but for right now, I want you to realize, what if I had this? H of x equals integral of 7 to x secant squared t times natural log of t dt. And I want to know what the derivative is. What's the rule say happens? Whatever that function is, that's the answer, but now you evaluate it at this. So it's just going to be, yeah, go ahead. Done. Done. Right? That's now a function and its derivative. That is now a derivative rule for if your function is the area function. This is the rule for its derivative. Just like when we have cosine, we learned its derivative rule. And that's the same idea. So now, truly the last thing. So what if I had j of x equals the integral from... Do you see how that doesn't matter where shit? They put a. So as long as that's a constant, everything's fine. So what if I did negative 110 to x squared, oh shit, of tangent t. Now here, what's on the inside of g? X. What's on the inside of j? X squared. What rule does that invoke? Chain rule. Chain rule doesn't give a shit what the thing looks like. Function of x, there's an x. Function of x, there's an x squared. Oh, the inside is more than just x. So what's the rule say? The rule says, take this, evaluate it at this, but then chain rule says, times the derivative of the inside. Chain rule doesn't stop working just because, oh, I made a brand new function based on something weird. Derivatives don't give a shit. Integrals don't give a shit. Chain rule don't give a shit. If the inside function is more than just x, chain rule comes in. Period. I like it, maybe, maybe. We did some weird shit today. Oh, we need to have a quiz. When's our next test? I forget. 26th? Oh, you think so? Nobody has their homework sheet with them? 29th? Okay. Alright, so let's have a quiz. We're going to quiz on next Tuesday instead of this Thursday. Or do you want to quiz on Thursday? Quiz on Tuesday. By the way, Monday's a holiday. You guys remember that? It doesn't affect us, but it affects if you take a Monday class. Quiz on Tuesday. You're going to like this. Section 47, 49, and 51. So none of the sum of I squared equals n times n, none of that yet. That's 5-2. 5-1 is where you do 6 rectangles or whatever. So that's on next Tuesday. Okay. That's plenty.